Good morning, everyone, and welcome to today's hearing. We're going to hear further presentation from one of the inquiry's experts. Yes, Mr. Millett.
Good morning, Mr. Chairman. This is the final day of the experts' presentations for this week. Today, Professor Luke Bisby, who sits on your right, will be explaining certain key scientific concepts relevant to flammability and to flame spread, and he will be describing the material properties of certain materials present in the facade and in the windows of Grenfell Tower. He will also set out the preliminary evidence which assists in understanding the pattern of flame spread out of flat 16 and over the exterior of the tower on the night of the fire. Before I call Professor Bisby formally, I should give certain trigger warnings about the content of his presentation. His presentation, and particularly this afternoon, will include a large number of images and videos and audio depicting the external flame spread on the night of the fire. That will include the playing of his composite flame spread video, which was played during my opening, and the detailed consideration of that and other flame spread material, which shows the building burning and on fire. Some of the videos include the audio of people witnessing the fire and their distress at the unfolding events. The presentation will also contain a number of images of the burnt-out tower after the fire and the playing of the first 999 call by Mr Kebede. So, Mr Chairman, I will now call Professor Bisby.
Thank you.
I do solemnly, sincerely, and truly declare.
And affirm that the evidence I shall give.
And affirm that the evidence I shall give.
Shall be the truth.
Shall be the truth.
The whole truth.
The whole truth.
And nothing but the truth.
And nothing but the truth.
Thank you.
Thank you. Professor Bisby, could you please give the inquiry your full name?
Luke Alexander Bisby.
And you have provided to the inquiry a written report which is dated the 2nd of April 2018.
That's correct.
And that report addresses the ignition of the facade materials and your preliminary conclusions on the fire spread to and on the exterior of the building.
Yes, it does.
And as you indicate in the declaration in section 1.6 of your report, you have provided it in the same way as you would have provided a report to a court.
That's correct.
In section 1.4 and appendix D to your report, you have outlined your background and your experience relevant to the matters in this inquiry.
Yes, I have.
I'm not going to ask you to repeat the detail of that today. We can take that as read. But in terms of key points, would you agree you are a Professor of Fire and Structures within the School of Engineering at the University of Edinburgh in Scotland?
That's correct.
And that prior to taking on your expert witness role for this inquiry, you were also head of the Research Institute for Infrastructure and Environment at the University of Edinburgh.
Yes.
You are a co-editor-in-chief of the technical and scientific publication Fire Safety Journal.
That's correct.
And you are, I think, chartered structural engineer with the Institution of Structural Engineers and a licensed professional engineer in Ontario in Canada.
That's correct.
You are also an active member of the UK Standing Committees on Structural Safety, or SCOSS, and Confidential Reporting on Structural Safety, CROSS, and a fellow of both the Institution of Fire Engineers and the Institution of Structural Engineers.
That's correct.
Are the factual matters set out in your report true to the best of your knowledge and belief?
Yes, they are.
And does your report accurately set out your opinions on matters relevant to this inquiry?
Yes, it does.
Thank you very much, Professor Bisby. Please do now go ahead and give your presentation.
Thank you and good morning. The Grenfell Tower fire initiated in the early hours of Wednesday, 14th June 2017, and continued for many hours with tragic effect. This catastrophic event resulted in 71 fatalities on that night and continues to cause immense trauma to the bereaved survivors and affected community. I'd like to begin my presentation by acknowledging this central, continuing, and human aspect of the fire. During the preparation of my report, I've reviewed harrowing evidence from victims, survivors, and emergency services, and I extend my deepest sympathies to those whose lives and loved ones were and continue to be caught up in this tragic event. As an instructed expert witness to the Grenfell Tower inquiry with a specific and technical remit, my Phase 1 report necessarily focuses on scientific and physical information and analysis related to the construction of the building and its external cladding. It is my hope that my Phase 1 report, along with the presentation and subsequent Phase 1 evidence, will help you, sir, as well as experts and lay people alike, to begin to understand, particularly in physical and scientific terms, how and why the Grenfell Tower fire of 14th June 2017 spread so rapidly and so extensively with devastating effect. My Phase 1 report is intended to serve two purposes. First, to provide an initial understanding of the ignition of the cladding materials at Grenfell Tower, and second, to set out preliminary conclusions on fire spread to and on the exterior of the building. During my presentation today, I will focus on presenting the preliminary evidence that I've gathered, rather than on my hypotheses and conclusions with respect to that evidence, although I will touch on these where necessary at this early stage of the inquiry's hearings. During my presentation today, I will focus on presenting, my preliminary evidence includes images and video submitted by members of the public. I'm particularly grateful for these, as without them my task would have been even more challenging. My preliminary evidence also includes evidence collected by the London Fire Brigade and the Metropolitan Police Service, information obtained from my own site investigations at Grenfell Tower, testing undertaken by various organisations, including the University of Edinburgh, on behalf of the inquiry, and information obtained by or provided to the inquiry from a range of organisations, including core participants to the inquiry. I've also drawn on my own background knowledge and on that of a core of my specialist colleagues at the University of Edinburgh, specifically Dr. Angus Law, Dr. Rory Haddon, and Emeritus Professor Dougal Drysdale. In addition, I've drawn on the academic literature and, in a limited number of cases, information which is publicly available via the World Wide Web. All of this information is referenced within my Phase 1 report and has been made available to the inquiry's core participants. For the benefit of yourself and the wider participants to the inquiry, I'd like to place my work for the inquiry within the context of the work being undertaken by the inquiry's other instructed experts. As Mr. Millett has previously explained, Phase 1 of the inquiry is intended to investigate the development of the fire itself, where and how it started, how it spread from its original location to other parts of the building, and the chain of events that unfolded during the course of the hours until it was finally extinguished or burned out. Phase 1 is also examining the response of the emergency services and the evacuation of the residents. For Phase 1, you asked me to provide a report on a subset of these issues. The first of these is ignition of the building's cladding materials, and if I may paraphrase, how did the fire get from inside the building out and onto the exterior cladding? My second task is to provide preliminary evidence on fire spread to and on the exterior of the building. And again, if I may paraphrase, how and why did the fire spread so rapidly and so extensively over all four faces of the building? My focus is therefore on the cladding materials, products, and systems at Grenfell Tower, and the rapid and extensive external fire spread. I will not comment extensively on the fire's origin and cause, the emergency service response, spread of fire and smoke within the building, or the building's evacuation. These are, of course, all critically important topics, but are being addressed by the inquiry's other experts. I will also avoid commenting on the regulatory compliance of the materials, products, and systems used at Grenfell Tower, as regards the applicable building regulations and guidance documents. In line with your instructions, my Phase 1 work has been concerned with identifying what aspects of the building design and construction played a significant role in enabling the disaster to occur. It is only by understanding the specific makeup of the cladding and the physical processes by which the fire spread over the building that you will be able to evaluate the relative roles of materials, products, and systems during the fire. To address the relevant issues, my presentation is structured in 3 parts. First, fire science. I will provide a brief overview of the fire science that is necessary to adequately understand the factors influencing fire spread to and on the cladding. This will also help to explain the potential contributions of different materials to exacerbating the speed and extent of the external fire spread. Second, cladding materials and products. I will describe in considerable detail the various materials and products used within the external cladding system, and briefly how each of these responds to heating from a fire. The third and final part of my presentation will focus on fire spread to and on the cladding on the night of the fire. I will revisit the video shown during opening remarks by Mr. Millett, and I will use this, along with other evidence, to provide a detailed summary of both the timelines and the physical mechanisms of fire spread. So part 1 deals with fire science. The first part of my presentation deals with 2 particular aspects of fire science that are central to what occurred at Grenfell Tower: flammability and flame spread. Together, these will help us to understand how the fire spread to the cladding and on the cladding. Both flammability and flame spread are intuitively understood by most people in general terms. However, I believe it's important to begin my presentation of my preliminary evidence by discussing their more precise technical meanings as well. Otherwise, developing a deep understanding and unpicking the causal roles associated with cladding materials, products, and systems is impossible. Flammability refers to the ease of ignition of a material and the manner in which it burns. The flammability of a material is governed by the physical properties of the material, its chemical composition, and to some extent, the manner in which its flammability is evaluated. A range of different flammability tests are used, both in the UK and internationally. Flammability is not a yes-no proposition. There is a gradation of performance amongst materials and products. Flammability is governed by a material's properties, its immediate environment, and its geometry. Flammability is not a yes-no proposition. Yes. Flame spread, however, is governed by a material's properties, its immediate environment, and its geometry. As with flammability, a range of different tests can be used to assess the flame spread on different materials and products. To interpret and understand the evidence of fire spread at Grenfell Tower, it's necessary to have a basic understanding of the physical mechanisms that govern both flammability and flame spread. I will avoid technical language and jargon to the extent possible. However, this is science, and the subject matter is rather complex. Indeed, highlighting the complexities of the science is one of the key things that I hope to accomplish today. The topic, therefore, demands a certain level of technical terminology. Fire. We all have a sense of what fire is, and a sense of which materials will burn and which will not. But fire is not, in reality, a single and simple process. Rather, it is the result of a sequence of interrelated processes that may occur when fuel, oxygen, and an ignition source are combined under the correct conditions. Fire is the visible flame, smoke, and heat produced by an uncontrolled combustion reaction. This results from a chemical reaction between flammable gases and oxygen, which makes up 21% of air. The combustion reaction occurs rapidly and is exothermic, by which I mean that it releases energy and we perceive this as heat and light. In the case of burning of solid materials, such as wood, plastics, or indeed insulating foams, the flammable gases which enter the flame are produced by a process of thermal decomposition. This process is referred to as pyrolysis. Gases produced by pyrolysis of the solid are flammable when they react with oxygen in the air and form gaseous products such as carbon dioxide and water vapor. In addition, very small solid particles are generated. These form the visible component of smoke or soot. In order for flaming to occur, the fuel must be in the form of a gas. This means that it's able to mix and react with oxygen from the surrounding air. And critically, this means that solids do not burn directly. Instead, it is the gaseous fuel produced by the thermal decomposition of the solid that is burning. This distinction may at first seem unimportant, but I hope that my reasons for making it become clear during the course of my presentation. The combustion of solids can be readily illustrated using the familiar example of a flame produced by the burning of a wooden matchstick, as I've shown here. Here I should like to say, sir, that while I'm going to use a matchstick to illustrate some of the key concepts of flammability and flame spread, in reality, the processes at play in the ignition and burning of a match are even more complex than I will be able to describe in my limited time today. The solid, in this case, is the wood from which the matchstick is made. Wood, as we all intuitively understand, is a combustible material. When wood is heated, in this case, by the flame from the match itself, the molecules that make up the solid wood thermally decompose and are released as flammable gases. By this I mean the wood undergoes pyrolysis. These flammable gases are transported into the flame by a buoyant flow due to the fact that hot gases rise. As the flammable gases are transported into the flame, they mix with oxygen, which is available from the surrounding air. We say that the surrounding air is entrained into the flame. Provided that sufficient heat is present within the flame and that the mixture of flammable gases and oxygen is in the correct proportions, the gases and oxygen will react. This reaction releases energy, which heats up the gases, which then radiate energy. This reaction also produces combustion products such as carbon dioxide, water vapor, and tiny soot particles, as I've already mentioned. It is the glowing, by which I mean the emission of thermal radiation and light, of these heated soot particles that produces the characteristic yellow flame we associate with fire. The flame can therefore heat objects by two processes of heat transfer: convection of buoyant hot gases, typically above the flame, as I've shown here, and by radiation to any materials that are within sight of the flame. In the case where the match is held horizontally, as shown here, it is radiation from the flame, shown there, and conduction along the matchstick, shown by that arrow, which heats the unburned wood. Conduction refers to the transfer of heat within the solid. This heating of the wood causes further release of flammable gases, and so on, in a self-sustaining process that we call fire. As I've just outlined, the process of thermal decomposition of a solid material is called pyrolysis. This process is endothermic, meaning that it requires a supply of energy from an external source in order to occur. Pyrolysis is fundamental to determining how, or rather if, a solid material will ignite and continue to burn, and the conditions under which this can occur. Pyrolysis, like any chemical reaction, is strongly temperature dependent in that higher temperatures result in faster pyrolysis. This means that the rate at which a solid can be heated will depend on its rate of pyrolysis. The rate at which pyrolysis occurs will then influence whether a flammable mixture of pyrolysis gas and air will form and sustain a flame. By this I mean that the rate at which pyrolysis occurs will dictate whether a material ignites and whether it will continue to burn. Not all mixtures of flammable gas and oxygen can burn. The gas and oxygen have to be in the correct proportions and in the presence of an appropriate ignition source. Those mixtures that can burn are called flammable mixtures. Furthermore, both the thermal properties of a material and its geometry play important roles in determining both its ignition and its burning behavior, and both are central to developing a physical understanding of what occurred at Grenfell Tower. I'd now like to discuss some particular technical concepts and terminology which relate to the heating of a solid material. When discussing the fire behavior of materials, it is conventional to differentiate between materials that are known as thermally thick and thermally thin materials. This distinction is based on the physical dimensions of the material properties, and the thermal characteristics of the surrounding environment. Essentially, a thermally thin fuel is one which heats uniformly and can be characterized by one temperature. In this case, the response of the material is limited by the transfer of heat from its surroundings. A thermally thick fuel is one which heats non-uniformly and exhibits an internal temperature gradient as energy is transferred into the body of the material. By this I mean that the surface of the material gets hot, but the interior stays relatively cool. In this case, the response of the material is influenced by the rate of heat transfer within the material via the process of heat conduction, as I've already mentioned. Thermally thin fuels ignite more readily than thermally thick fuels, all other factors being equal. A familiar example of thermal thickness can be understood by comparing the ease of ignition of wood shavings versus a solid block of wood. Both are composed of the same material, wood. However, the wood shavings are thermally thin and can be readily heated such that ignition occurs. The large block of wood, however, is thermally thick, and when exposed to a flame, the heat is conducted into the block and away from the surface, thus making it harder to ignite. The difference between these two cases, as regards both ignition of a material and the chances that it will continue to burn, are shown in these side-by-side videos of wood shavings and a block of wood, in both cases ignited by a match. And I'll play this now. And you can see actually multiple attempts to ignite the block of wood with subsequent matches. You get the point, I hope. For a thermally thick fuel, when exposed to a heat source, the surface temperature of the solid material will begin to increase. The rate of increase is determined in part by the physical properties of the material. The key parameters in this situation are, first, the thermal conductivity of the material. This is a measure of the ability of the material to transfer thermal energy internally by conduction. Second, the density of the material, and this is a measure of the material's mass per unit volume. And third, the material's specific heat capacity. And this is a measure of the amount of energy required to increase the temperature of 1 kilogram of the material by 1 degree Celsius. A heat transfer analysis can show that the product of these three parameters, thermal conductivity multiplied by the density multiplied by the specific heat, governs the rate at which the surface temperature of a solid material increases when exposed to a heat source. This is called the thermal inertia of the material. And it represents, if you like, the ease with which the surface temperature of a material will change when exposed to heating. Materials with a high thermal inertia, such as metals, for example, are comparatively slow to heat at the surface, all other factors being equal. Conversely, the surface temperature of a material with low thermal inertia, such as polymer foam insulation, for instance, will increase rapidly when heated. As I've already stated, pyrolysis is a temperature-dependent process. Thus, there is a strong coupling between heating of the solid and pyrolysis. Consequently, materials with a low thermal inertia, where the surface will heat more rapidly, will initially experience more rapid pyrolysis than materials with higher thermal inertia. It's very important to understand this because it helps us to understand and hopefully eventually to quantify the potential roles of the various materials and products that made up the cladding at Grenfell Tower. As a result of the factors that I've now described, it's common to assume a pyrolysis temperature at which pyrolysis will occur for a given material. All other factors being equal, materials with higher pyrolysis temperatures are more difficult to ignite than those with lower pyrolysis temperatures. Let me now turn my attention to the issue of flammability. On a day-to-day basis, we tend to think of materials as either being flammable or not, or as being either combustible or not. Indeed, the word combustible has received a great deal of attention of use in the media since the Grenfell Tower fire. In reality, for materials that have the potential to burn, by which I mean those materials that are combustible, flammability is a relative rather than absolute property. Depending on the circumstances, therefore, combustible materials can either be more or less flammable, and this distinction is actually very important. In a regulatory context, material flammability quantifies the degree to which a material will burn with a flame under specified conditions. Material flammability tests therefore allow different materials to be ranked as regards their suitability in certain applications, based on results from tests in standardized test apparatus. It should be noted, however, that material flammability parameters are not fundamental material properties. This is precisely because they depend on the method of evaluation. Flammability testing outcomes may be influenced by a range of phenomena, and I believe it's worth taking a bit of time now to discuss these in general terms before moving on to look at the specific materials, products, and systems that were installed in the cladding at Grenfell Tower. First, ignition. In the context of most fire safety applications, ignition is defined as the initiation of what is known as gas phase combustion. By this I mean sustained flaming or burning of pyrolysis gases in the manner I described earlier using the photo of the wooden matchstick. Ignition is the moment that the visible flame first appears. Whether ignition of a solid material occurs in a given situation is strongly time dependent. This means that ignition only occurs after a period of heating of the solid such that its surface temperature reaches the pyrolysis temperature, and flammable gases are produced by pyrolysis in sufficient quantities to sustain a flame. Common ignition tests used in practice apply a radiant heating source to heat a material. The magnitude of the heating is defined in terms of what's called the incident to the wood would actually be insufficient to continue to generate the necessary pyrolysis gases, and the flaming combustion would stop. The flame would go out. Higher heat fluxes therefore lead to more rapid ignition, all other factors being equal. As I've already discussed, the rate of heating for thermally thick fuels depends strongly on the thermal inertia of the material. The time to ignition under a given heat flux exposure is therefore also strongly dependent on the thermal inertia of the material. Materials with low thermal inertia, for example, polymer foams, heat rapidly at their exposed surfaces, generally resulting in short times to ignition. Materials with higher thermal inertia, for example, common synthetic polymers, which we more commonly call plastics, have longer times to ignition. It follows from the preceding discussion that there is a level of heating, by which I mean a level of heat flux, below which ignition will not occur for a given material when tested in a given configuration. This is called the critical heat flux for ignition. Materials with low values of critical heat flux for ignition are, in general, easier to ignite than those with high values of critical heat flux for ignition. Understanding how materials ignite is essential, for instance, in order to confidently suggest how the fire at Grenfell Tower spread from within the kitchen of flat 16 onto or into the cladding adjacent to the kitchen window. The ignition properties of a material are also critical in evaluating their ability to spread flame, for reasons that I will discuss in a few minutes. Before doing so, however, I'd like to discuss heat of combustion. Once a material has ignited, the primary variable of interest is the rate at which energy continues to be released, since this is what drives the growth and spread of a fire. The total amount of energy that is available to be released from a material is known as its heat of combustion. This is a measure of the total energy that can be released per unit mass of a material under optimal conditions for combustion. The rate at which energy is released, however, and the fraction of the total available energy that actually is released under a given set of circumstances is a function of its heating conditions, its geometry, and its orientation. This distinction is critically important because, as I've already suggested, just because a material can burn under some circumstances doesn't necessarily mean that it will burn under a particular set of circumstances. And this idea will be familiar to anyone who has attempted to start a log fire without using kindling. Just because wood can burn doesn't mean it always will. The heat of combustion of a material is measured by burning a unit mass of material in an atmosphere of pure oxygen. This increased reactivity of this atmosphere compared to air, which, as I've already noted, is only 21% oxygen, results in complete combustion of the material and the conversion of virtually all of the stored chemical energy into thermal energy. The heat of combustion thus provides an upper limit on the amount of energy that can be released by the burning of a material. However, the heat of combustion on its own does not give any information regarding the rate at which energy is released after a material is ignited, nor does it account for the heat transfer processes that lead to ignition, the material geometry, or the physical changes that may occur, all of which also affect a material's burning behavior. To give you a sense of the variability of heats of combustion amongst materials, this chart shows the heats of combustion of a number of familiar and not so familiar but relevant materials on this chart. Materials with gray bars are common and in some senses familiar, but are not considered significant as regards my preliminary evidence related to the Grenfell Tower fire. These are shown because these materials may be familiar to you, you may have some understanding of how they react to heating. Whereas materials in red are less familiar, aside from wood, of course, but were present in significant quantities within the cladding system at Grenfell Tower. You may note the broadly similar values for the synthetic polymer or plastic materials, polyethylene and polystyrene, as compared with diesel fuel, for instance. I'll return to this point later on. Next, heat release rate. As I've mentioned, the rate at which energy is released from a material, by which I mean whether the available energy is released quickly or slowly in a given set of circumstances, is described by the heat release rate. The heat release rate describes the rate of energy release per unit time as an object burns. Objects made from materials with the same heat of combustion may burn in very different ways once ignited. At a material level, the heat release rate behavior is dictated to a large extent by the pyrolysis behavior of the solid material. If the material melts, such as in the case of the synthetic polymer material polyethylene, for example, then after ignition, the heat release rate will increase to an essentially steady value until virtually all of the material is consumed. And this is illustrated schematically in the left-hand figure shown here. This is a key point, and I'll return to burning of polyethylene, which I abbreviate in some cases PE, later in my presentation. If, however, the material chars, such as in the familiar case of wood or the less familiar case of a thermosetting polymer foam insulation, which I will also return to later, then under most conditions there will be an initial period of high heat release followed by a period of lessening heat release rate. This is due to the formation of a protective char layer on the surface of the material, and this is illustrated in the right-hand figure shown here. The formation of the char layer decreases the rate of energy transfer into the material, and hence reduces the rate of pyrolysis and therefore the quantity of flammable gases produced. The heat release rate of a material also depends, again, on its physical geometry and surrounding conditions, and on the presence of any external heat sources. The heat release rate of an object burning in the presence of an external heat source, such as a large fire, will be a strong function of the magnitude of the external heat source for the reasons I've already discussed. The heat release rate is therefore important for evaluating the fire hazard associated with an object. This is because it determines the energy released from a material that is available to be transferred back to the fuel, thinking again about my match, thus creating a feedback loop which may sustain the flaming. Materials with a high heat release rate therefore typically result in more rapid fire growth and/or fire spread. And so the growth and spread of fire are obviously of fundamental importance to this inquiry. So finally, having discussed these foundational concepts of fire science, I will turn to flame spread. Flame spread occurs when sufficient heat is transferred from a burning region to an adjacent unburnt material region. The rate at which a fire will grow depends in part on how rapidly flame can spread on the surface of the material. Flame spread is strongly influenced by the physical configuration of the system, such as its material geometry and orientation. The process of flame spread is most easily thought of, very helpfully in my opinion, as a series of localized ignitions. And the process required to sustain flame spread are thus the same as those that I previously used to describe ignition. So, as already discussed for ignition, sufficient energy must be supplied to the combustible solid ahead of the flames to heat the material such that pyrolysis occurs and flammable gases can be released. As the area where the pyrolysis is occurring advances, so too does the flame that we can visually observe. This is flame spread. It's common to distinguish between what is known as concurrent flame spread and opposed flow flame spread. Concurrent flame spread occurs when the flame spreads in the same direction as the flow of air. I'll show examples in a moment. Opposed flow flame spread occurs when the flame spreads in the opposite direction to the flow of air. These two extremes are commonly observed when a flame spreads upwards, which we call concurrent flame spread, or downwards, which is a case of opposed flow flame spread. Because of the importance to my phase 1 scope of work and to the preliminary evidence that I will present later today, I'm now going to describe in some detail the key processes associated with upward and downward flame spread. I will also describe horizontal or lateral flame spread. This is in fact a special case of opposed flow flame spread, as I'll explain in a few minutes. My discussion of flame spread draws on many of the fundamental concepts that I've already described. And hopefully you can see this is all building. The rate of flame spread is dependent on the heat transferred to the material and the material's thermal inertia. This is because the rate of flame spread is governed by the rate at which the material adjacent to the burning region can be heated to its pyrolysis temperature. Upward flame spread is generally faster than downward flame spread. This is because in upward flame spread, the flames and hot gases, which rise due to the effect of buoyancy, as I've already mentioned, will preheat the material ahead of the advancing flames. This preheating does not occur in downward flame spread, which is therefore slower. When considering the flame spread on synthetic polymers, which are more commonly called plastics, as I've mentioned, it's important to consider the effects of melting and deformations associated with their softening. Melting and dripping significantly complicate flame spread processes by removing material from the system, and with it, some of the available energy to drive flame spread. And I'll demonstrate this in a moment. So in a moment, I'll show a short video that shows ignition and upward flame spread on a vertically oriented matchstick. I will use this simple, familiar example, again, because of its intuitive value in demonstrating the relative physics, or the relevant physics, sorry. In upward flame spread, the heat transfer to the unburnt material ahead of the burning region increases the size of the burning zone, and hence the flame spread rate. The flame and pyrolysis products produced by the burning of the material rise due to buoyancy and heat the surface of the material, and this results in high rates of heat transfer to the surface of the material. As the unburnt material ahead of the burning region is heated, it begins to pyrolysize and generate flammable gas. As the gas ignites, the visible flame spreads rapidly. Typically, but not always, the rate at which the pyrolysis front advances is faster than the rate at which fuel is consumed. This is an important point. And consequently, the burning region becomes larger, producing flammable pyrolysis products at an increasing rate. This can be seen in my video in a moment, as the bottom of the match you'll see is still burning as the top ignites. The flame becomes larger and thereby increases the height of the heated material, which further increases the burning area. This positive feedback loop results in a self-accelerating process and rapid upward spread of flame. The sequence of events is shown in this short video. My next short video shows downward or opposed flow flame spread on an otherwise identical vertically oriented matchstick. In the case of downward flame spread, the rate of heat transfer to the unburnt material is much less than in upward flame spread, as I've already described. Consequently, the length of the preheated zone is much smaller, resulting in a smaller pyrolysis region, a smaller volume of evolved pyrolysis gases, and a much slower rate of flame spread. Indeed, in this case, flame spread eventually extinguishes rather than continuing to spread downwards. This sequence of events is shown in this short video. And you can just see the flame creeping down the matchstick very slowly. And there you can see insufficient pyrolysis gases being released to sustain the flame. A further special case of opposed flow flame spread is horizontal or lateral flame spread. This is similar to downward flame spread, and my next video shows the flame spreading from right to left. In this case, the rising hot gas draws air into the flame from left to right, hence referring to this as opposed flow flame spread, as in the case of downward flame spread. The heat transfer from the flame to the match is higher than in the downward case, as evidenced by the spread of the flame horizontally along the match. In this case, the rate at which the pyrolysis front advances is approximately equal to the rate at which the solid fuel is consumed, as evidenced by a steady movement of the flame from right to left and a flame with a reasonably uniform size. And I'll show this here. And that flame just continues to the left and off the screen. Now, of course, matchsticks don't melt and drip. This is not the case, unfortunately, for all materials. Rapid downward vertical fire spread may occur due to melting and dripping, in particular for certain synthetic polymer materials. When heated in a vertical orientation, molten, possibly burning material may flow downwards. Flame spread by this mechanism is governed by the viscosity of the molten material. If heated sufficiently, the molten material may also form burning droplets which may fall downwards. Both of these processes are clearly visible in my next video clip, and both may contribute to the formation of pool fires below and in front of the burning material, as is also clear from my next video. This slide shows a vertically oriented sheet of a white-colored polymer. In fact, the particular polymer used here is polyethylene. And the sheet is 3 millimeters thick, and I should point out that this is a demonstration, not a scientific test. The sheet has been ignited at its base using a butane torch, and this butane torch is just barely visible as a blue flame to the bottom left of the sample. And it's quickly withdrawn out of frame. And I'll play this clip in 3 segments. In the first segment, we see that a few seconds after ignition, the molten material is already beginning to fall down and burn on the floor beneath the sample. At this point, the flames on the polyethylene are relatively small. In the second segment, which begins about 3 minutes later, we see that the sample is burning on both sides and that there is an almost constant flow of molten, burning polyethylene falling from the sample to the floor. And I should point out that the vertical streaks are rivulets of melted, burning polyethylene. In the third segment, which begins about 6 minutes later still, the sample has been significantly consumed and molten polyethylene continues to fall. The fact that polyethylene burns in this manner is not at all surprising. This behavior has been well known and documented in the scientific and technical literature for decades. This particular issue will become very important later in my presentation when I discuss the fire spread that was observed on the exterior of Grenfell Tower. I've now spent considerable time discussing the most important fundamental fire science concepts and terminology relevant to developing a physical understanding of the circumstances of external fire spread during the Grenfell Tower fire. It is very important to note that my presentation of concepts such as ignition, burning, and flame spread relate primarily to single materials rather than to composite products. By this I mean products that are composed of a combination of materials, all of which may display substantially different flammability and flame spread properties. I should also note that very little useful fundamental experimental data are available in relation to flammability and flame spread on composite products, since most of these products violate the basic assumptions of many of the existing experimental and compliance testing methods. And this issue is of particular relevance to this inquiry, not least because of the large number of other buildings in the UK and internationally that are apparently clad using similar materials and products to those used at Grenfell Tower. Despite this disclaimer, a series of useful conclusions can be drawn on the basis of the discussion provided in this first section of my presentation today. And these are as follows. Ignition, flammability, flame spread, and fire growth are all influenced by numerous factors, including material properties, chemical composition, orientation, geometry, and interactions with other materials. Upward flame spread on a solid fuel is rapid because the hot flame and gases preheat the material ahead of the burning zone. Downward and horizontal flame spread is generally slower because preheating of the fuel ahead of the flame front is greatly reduced. Almost all of these concepts are important in order to understand even my most basic matchstick demonstrations of some of the relevant flame spread mechanisms. On this slide, I've placed all three of the matchstick videos, and I'm going to run them concurrently so that you can see just how important the relevant phenomena are as regards both the rate and the extent of flame spread. However, as I've just mentioned, downward flame spread may also be significantly influenced by melting and dripping of burning material, as I showed a few moments ago with reference to polyethylene. In all cases of upward, downward, and horizontal flame spread, the spread is dominated by the heat release rate of the existing fire, how the resulting fire transfers heat to the unburnt material, and the thermal properties of the material itself. Sir, that concludes my summary of the key fire science concepts and processes to which I'd like to draw your attention at this early stage of the inquiry. All of these concepts must be kept clearly in mind when considering the rest of the preliminary evidence that I will present today and indeed during phase one.
Thank you very much.
Mr. Chairman, I wonder if that's a convenient moment for the break.
I think it would be a good moment. Shall we break now and resume at 11:10, please? Thank you. Yes, Professor Bisbee, when you're ready.
Thank you. As I've already described, the orientation, thermal properties, and chemical composition are all important in understanding how materials and products may respond to fire. During this second part of the preliminary evidence that I will present today, I'll describe the materials and products used in the refurbishment cladding system at Grenfell Tower. I will describe where they can be found on the building and how they're arranged. I will also describe how they burn. The summary of materials and products presented in this section is based on a range of sources of evidence as follows. 4 post-fire inspections of Grenfell Tower that I've conducted prior to submitting my Phase 1 report, a range of documentation and photos made available to the public inquiry via formal disclosures, and materials and product samples taken from Grenfell Tower by the Metropolitan Police Service and provided to me for small-scale materials testing at the University of Edinburgh. Before I describe the materials in detail, I'd like to ensure that I'm clear about the terminology that I will use to describe different parts of the building. I will do this by presenting a number of annotated photographs and drawings to identify the terminology for parts of the exterior of the building that are relevant to my preliminary evidence. This image shows a portion of the west face of the building following the fire. This photo was obtained by the Metropolitan Police Service using a drone on the 25th of July 2017. During my presentation, when I refer to columns, these are the areas of building indicated on this image. I should like to point out that the east and west faces of the building each have 4 column lines, as shown here, whereas the north and south faces of the building each have 5 column lines, as noted by Mr. Millett during his opening remarks. When I refer to spandrels, this is a generic term that I use for the parts of the building between the windows, as indicated on this image. I also use the terminology spandrel section to refer to the building exterior between the column lines, the sections shown here. When I refer to rain screen cassettes, these are the external panels as indicated on this image. For example, here are spandrel section rain screen cassettes, and here on the column sections of the building. It's worth noting that these are gray in color from level 4 upwards. When I refer to the window sections of the building, these are the sections of the building as shown indicated on this image. Within the window sections, there are several individual components, including windows, extract fans, and mounting panels, and window infill panels. I'll describe these in a moment. When I refer to window infill panels, these are as indicated here in yellow. These are unglazed sections of the window units. It's worth noting that these are white in color from level 4 upwards. The kitchen windows are indicated on this image. And here I'd like to draw your attention to the fact that the kitchen windows are actually made up of 3 separate areas, and I'll describe each of these in more detail in a few moments. When I refer to cavity barriers, which would be very rarely, these elements are running vertically and horizontally within the cladding on the building, as indicated on this image, and visible only where the rain screen cassettes have been damaged or removed during the fire. You can just see them as the ragged lines underneath the yellow bars. And when I refer to the floor slabs, I'm referring to the structural reinforced concrete floors within the building, and these are at the levels approximately indicated by the yellow lines on this image. I will now describe the cladding system and its geometry in more detail by zooming in on one specific part of the building, specifically the section shown of the building's exterior, which I'm showing here This part of the exterior has the same arrangement of windows. Sorry, there it's zoomed in. This part of the building has the same arrangement of windows as those around the external east wall of flat 16, which is acknowledged by at least 3 of the inquiry's experts as the room of fire origin. The internal layout of this particular flat is also the same as that in flat 16, approximately, so that this is a kitchen window. The kitchen window is on the left, and the 2 rooms to the right of the kitchen window are associated with the living room. I'll now zoom in even further to look only at the region around the kitchen window, which is shown as highlighted there. Here I've highlighted one of the kitchen windows in the vertical line of flats in the tower ending with the number 3. These are flats positioned in the southwest corner of the building. I will now zoom in even further to the kitchen window specifically. The window comprises a large glazed window pane, which operates in both an inward tilting or inward turning, by which I mean swinging, manner, and hinged on the right when observed from outside the building. An extract fan, which is mounted within an infill panel, and this infill panel appears to be made from the same materials and construction as the window infill panels that I noted previously, and I'll come back to these in a moment. And a small glazed window pane beneath the extract fan and mounting infill panel, which operates in an inward turning manner and is hinged on the left when observed from outside the building. I'd now like to look in some detail at the composition and geometry of the cladding in various locations around this kitchen window, which has the same design as the kitchen window of flat 16, as I've mentioned. To do this, I'll use my own hand-drawn sketches of the relevant sections through the building. And these are based on my own post-fire investigations at Grenfell Tower, and I'll do this in the hope that my sketches will be more easily understood by you and by the other parties to the inquiry. I will necessarily be covering some of the ground already covered by Dr. Lane and Professor Nick Day. However, I believe that this is a useful repetition and that a detailed focus on the cladding materials and geometry is warranted under the circumstances. It should be noted that my sketches are only indicative and are not to scale. I should also like to note that my post-fire inspections at Grenfell Tower have confirmed that there is local variation of the refurbishment cladding geometry due to the geometry of the existing building and the presence of the original window openings. I've carefully considered this variability in examining the available evidence and drawing my preliminary conclusions. In my sketches, I will not show the location of cavity barriers within the cladding. And this point has already been discussed in some detail by Dr. Lane, and I don't consider it critical to my own scope of work. So let me look now in detail at the cladding immediately above and below the kitchen window opening. Please imagine if I were to cut through the cladding along a vertical line, as shown here, and then look inside the cladding to see the various layers that I cut through. I will look specifically at the cladding materials and geometry here, above and below the kitchen window. This slide, the following slide sequence shows the buildup of the different cladding materials, starting with the pre-existing or original cladding construction and adding the various components of the refurbishment cladding as I go. This slide shows a sketch of the original concrete construction at the location of the kitchen window, and remember, this is over a vertical slice through the building. The left-hand side of this image shows the outside of the building, and the right-hand side is inside the flat. Please note that I've removed the window pane and brought these 2 sections closer together vertically in this drawing than they actually are in reality. The original concrete structure can be seen in gray. The concrete slab that forms the ceiling is shown top right, and the concrete wall below the windows is shown below. There were also original timber battens and a window framing board, and pearl board foam insulation both on the ceiling in a band and on the interior wall. I'll describe these more in more detail shortly. The original windows were located approximately as shown here. Below the windows, the purl board insulation was covered by a sheet of gypsum plasterboard as an internal finish within the flat. During the 2012 through 2016 refurbishment program, the original windows were removed, and installed over top of this original construction was the refurbishment overcladding system. This comprised supporting aluminium rails and fixings, which were anchored into the pre-existing reinforced concrete floor slabs and spandrel beams. The polymer foam thermal insulation was applied in 2 layers on this section of the building, each 80 millimeters in thickness. And the aluminium composite material, or ACM rain screen cassettes, were then applied. Between the rain screen cassettes and the foam insulation was an open ventilated void, hence the terminology ventilated rain screen cladding system, to describe this particular type of cladding. And I'm referring to the voids shown with writing there. The new aluminium framed double glazed windows, extract fan units, and window infill panels were fitted into the openings and mounted on the aluminium rails, as shown here. And you can see here how I've cut and reduced the vertical size of the window. Inside the building was placed some additional polymer foam insulation in approximately those locations, and a finishing detail of a UPVC window board, which was bonded in place using a polymer adhesive, as shown there. Any small visible gaps were then filled with a silicone sealant. UPVC stands for unplasticized polyvinyl chloride and is a specific type of polymer, i.e. a plastic, material that I will describe in more detail later in this presentation. We will look at each of these materials and products in more detail in a moment, but for now I simply wanted to show their locations within the cladding. Please note that the location of the glazing has been moved outwards as a consequence of the recladding, and that the windows themselves now sit some distance outside the original reinforced concrete construction. I'd now like to take a horizontal slice through the building and look at the cladding build-up immediately to the left of the kitchen window when viewed from outside the building, at this location here. When viewed from inside the building, this slice is across the window as shown in this image. Please note that the dark material on the windowsill in this photo is debris from the fire. This is a partially fire-damaged flat. In this photo, the UPVC window boards are clearly visible, as are the lines of silicone sealant used to fill the gaps between them, here. Please also carefully note this thin strip of UPVC window board, now highlighted in yellow. This has been installed in order to fill what would otherwise be a gap between the new refurbishment window frame, and the pre-existing window opening within the original reinforced concrete facade, as I'll show in a moment. This appears to be held in place with a bead of silicone sealant. Cutting through the wall of the building at this location and looking from the top down, you can see a portion of the octagonal-shaped reinforced concrete column on the left side of this sketch. Inside the building is at the top of this slide, and outside the building is at the bottom. Again, the original construction included timber battens and timber window framing board, and the original single glazed windows within aluminium frames. Here the line showing the glazing fades at the right, and this is to indicate an indefinite distance in this direction in my sketch, so the window continues off to the right. As before, the original windows were removed, And the new double glazed windows were installed on the horizontal aluminium rails, which I showed previously, but which are not shown in this view. In this location, to the left of the window, i.e. on the column, the overcladding comprised the polymer foam thermal insulation, in this case, a single layer, 100 millimeters thick, and the ACM rain screen cassette. As highlighted a moment ago, in this location, there was a gap between the edge of the new window frame and the pre-existing reinforced concrete column. There's a void in the rain screen, and that is the gap that I'm referring to. A weatherproofing membrane made of EPDM rubber sheet was positioned across the gap formed in this location. Foam insulation was present both on the inside and outside of this gap, as shown there. And the UPVC window board was again applied as an internal finish, as shown there. I should like to note at this point that the specific geometry of the small section of polymer foam insulation directly outside the kitchen window, that's the strip of UPVC window board that I highlighted a moment ago. And the small section of polymer foam insulation directly outside the kitchen window, which is now highlighted, appears to have varied over the building. In some cases, the insulation boards were cut differently at this location. And in some cases, the smaller pieces of foam insulation immediately outside the EPDM rubber membrane appear not to have been installed at all. This is important as regards potential routes for fire spread from inside the building to the cladding. As I will discuss later today, this is an ongoing item for investigation. Moving lower down to the spandrel section of the exterior cladding below the kitchen window, I will now take a horizontal slice across this part of the building, in this location shown here. In this location, again, looking down at the surface of my slice through the building, we can see the original concrete column and spandrel beam. Here, again, the spandrel beam fades at the right to indicate that in reality it continues to the right. There are 1 or 2 layers of PIR foam insulation, depending on the location on the building. On the columns, 1 layer was present with a thickness of 100 millimeters. This is shown here. Whereas on the spandrel, as I've already noted, 2 layers, each of 80 millimeters in thickness, were present. Aluminium cladding rails support aluminium cladding rails, shown here, support the spandrel ACM rain screen cassettes, as was described in detail by Dr. Lane on Monday. These were attached to the refurbishment window frames using a series of metal brackets not shown in this view. And here are shown the connection to the ACM rain screen cassettes on the cladding rails. Spray foam was used liberally to fill gaps and small voids within the external cladding system. Aluminium tape also appears to have been used liberally within the cladding. And finally, the ACM rain screen cassettes were hung from the cladding rails. And again, please note the void within the cladding between the rain screen cassettes and the PIR foam thermal insulation. I'd now like to draw your attention to a particular feature of the cladding geometry that exists along the vertical line where the spandrel sections of the building meet the column sections of the building. Remembering that the 2 horizontal sections that I've just taken through this location and where they're positioned in the building, both through the window section and through the spandrel section, which is shown here, I've identified that a continuous vertical void exists within the cladding at the location shown in this figure. This void is continuous on all columns from level 4 all the way to the top of the tower. If I show the location of these voids on the column to the left of this particular kitchen window, I should note that it's the same on all columns as far as I can tell at this point, they are as shown here. If I show these voids on a section of the full west face of the tower, they are as shown here. The final part of the cladding that I'd like to examine in detail is at the location that I have called the column tip in my Phase 1 report. This is highlighted in yellow in this figure. I wish to highlight this both for completeness and because of another particular feature of the cladding geometry at this location, that location just there. This image shows a sketch of a horizontal slice across the column tip, as shown by the dashed line in the previous slide, and again looking down at the surface of my slice. The tip of the original concrete column's external precast concrete surface is seen in gray. The overcladding in this location comprises the aluminium fixings and rails, shown here, the single layer of foil-faced PIR foam insulation, 100 millimeters in thickness, and the ACM rain screen cassettes, again with a ventilated rain screen cavity. Within the cladding rail at the column tip, I've identified that there is another uninterrupted void that spans the entire height of the building. The location of this void, rather, is illustrated here. Again, if I show these additional column tip voids on a section of the full west face of the tower, they are as shown here. Combining these with the continuous vertical voids discussed previously here, we can see that the column lines in particular provide numerous vertical voids and channels that run uninterrupted from at least level 4 right the way to the top of the building. Sir, I've now described my key preliminary evidence with respect to the geometric arrangements of the cladding. Having dealt with the geometry, I will now describe the various materials and products that were present within the cladding system of Grenfell Tower at the time of the fire. Before I begin, I believe it's important to make clear a distinction between materials and products. Materials are comprised of, well, a single material. Products, on the other hand, can be comprised of multiple materials. For example, aluminium is a material, and polyethylene is a material. However, Reynobond PE, shown here for instance, is a product consisting of 2 aluminium sheets separated by a gap which is filled with polyethylene. Even at this early stage of the inquiry, Reynobond PE will no doubt be familiar to you, and I will discuss this product in more detail in a few minutes. It has been common to refer to Reynobond PE and similar rain screen products as aluminium composite materials, or ACMs. The use of the word material in this context is, in some ways, a misnomer. However, because the word composite precedes the word material, the name tells us that this is actually a product consisting of multiple materials. Another example of a product is Celotex RS5080, which is shown here. This product is composed of several materials: polyisocyanurate, or PIR foam, which is highlighted here, a thin aluminium foil facing, which is shown here and is on both sides of this material, and a glass fiber mesh, which sits within the PIR foam, as indicated by the lines shown here. I will also return to the product Celotex RS5080, which is part of the Celotex RS5000 range of insulation products, later in my presentation. With this distinction between materials and products made, I will now move on to describe the different cladding materials and products used on Grenfell Tower and their respective locations within the cladding system. and I apologize, this does get a bit repetitive in this section of my presentation. ACM rain screen cassettes were provided on both the spandrels and columns of Grenfell Tower, as highlighted here in yellow. ACM products were also used to form the ornamental architectural crown at the top of the building, as shown here, with substantial fire damage from a drone photo taken after the fire on the 25th of July 2017, with much of the crown now missing. The crown elements would have been configured approximately as I've shown them here before the fire. The specific geometry and materials of the architectural crown are discussed in detail in my Phase 1 report and will be the focus of considerable additional work at Phase 2. For my presentation today, it's sufficient to note that the architectural crown was comprised largely of closely spaced, vertically oriented, C-shaped channels formed from ACM panels. These were mounted on closely spaced aluminum rails, which were supported off the original reinforced concrete parapet beams at roof level. As we heard on Monday, the ACMs at Grenfell Tower were a product called Renabond PE, where the PE stands for polyethylene. This was and is manufactured and sold by Arconic Architectural Products. This image shows the corner of a Renabond PE panel taken from Grenfell Tower after the fire and provided to me by the Metropolitan Police Service. It is comprised of a 0.5 millimeter thick aluminium outer surface, which is bonded to a 3 millimeter thick polyethylene filler material and a 0.5 millimeter thick aluminium inner surface. To form the product into rain screen cassettes, flat sheets of the material are cut and folded. This image shows various different cuts and folds in a typical ACM rain screen cassette taken from Grenfell Tower after the fire, and again, provided to me by the Metropolitan Police Service. I would like to draw your attention to the exposed edges of black polyethylene material that this image reveals. This image is showing the back of a typical rain screen cassette, by which I mean it is showing the face of the cassette that would have been looking into the ventilated rain screen cavity. The black areas in this image therefore present surfaces of polyethylene that would be directly exposed to any flame or heat within the cladding cavity, should a fire penetrate by essentially any means into the cladding system. Two different colors of polyethylene are present in the Renabond PE ACMs used on Grenfell Tower. The black polyethylene that I've shown here, or a light-colored translucent polyethylene, which I've not shown. Testing will be undertaken at the University of Edinburgh to assess if there are any discernible differences between these two different colors of polyethylene in terms of their reaction to fire. Next, I'd like to look at the PIR foam insulation products that were used at Grenfell Tower, where PIR again stands for polyisocyanurate. Some of these products are also visible in this image. In the locations where the ACM cassettes, again, have been damaged or removed by the fire. For instance, we can see some insulation here and here. Most of the PIR foam in this photo has had its external aluminium skin removed and has been charred on its outer surface during the fire, thus having a darkened, cracked, blackened appearance. This charring behavior is significant as regards the manner in which PIR foams may burn, and I will return to this point later in my presentation. Just to remind you, the locations of the PIR foam on my sketches of vertical slices through the building are illustrated in yellow here, where you can see where PIR foam is located both above and below the window and within the window surround. And again, here around the column to the left of the window in my horizontal slice. This image shows a piece of the PIR foam taken from one of the columns at Grenfell Tower, and again provided to me by the Metropolitan Police Service. Visible in this photo are the PIR foam, which is yellow in color, and one of the foil faces. I should note that the bottom surface of this product also has a foil face, but it's not visible in this photo. This insulation product is manufactured by Celotex under the generic product name RS5000. The specific product name is Celotex RS5100, where the last three digits, 100, correspond to the thickness of the product in millimeters. This image shows a piece of PIR foam insulation that was taken from one of the spandrel sections at Grenfell Tower. Again, visible are the PIR foam, again yellow in color, the foil faces, again top and bottom, and in this particular product, a glass fiber weave within the PIR in 2 layers, as noted earlier. This product is also from the Celotex RS5000 PIR insulation product range, and at Grenfell Tower, this product was anchored to the concrete spandrels in 2 layers, each of 80 millimeters thickness, as I've mentioned. The specific product name is therefore Celotex RS5080, where again the 80 represents a product 80 millimeters thick. Also on this photo, we can see some of the polyurethane polymer spray foam that was present in comparatively small volumes, I should say, in many locations within the cladding. In addition to the PIR insulation identified during post-fire inspections at Grenfell Tower, phenolic foam, or PF insulation, has also been found on some areas of Grenfell Tower. This product, the phenolic product, is not shown here, has been identified as Kingspan Cooltherm K15, and based on the available evidence accounts for only a very small proportion of the insulation and only on a small number of spandrel sections of the building. 2 further PIR foam insulation products have been identified during my post-fire investigations of the undamaged and partially damaged sections of the building. These were located around the window framing of the refurbishment windows, as I've mentioned, and are shown in this photo, again provided to me by the MPS. A 25 millimeter thick foil-faced PIR polymer foam insulation board manufactured by Celotex. This is shown top right on this slide and has yet to be definitively identified. And a 25 millimeter thick foil-faced polymer foam insulation board manufactured by Kingspan. This is shown bottom left. The specific product name is yet to be confirmed, although based on its markings, it is likely to also be PIR foam and from the Kingspan Therma product range. I've previously mentioned an insulation product called Pearl Board. This appears to have been part of the original construction of Grenfell Tower and was located inside the building, both above the window on the ceiling, as shown here, and in a continuous band around the perimeter of all flats, and below the window on the inside face of the reinforced concrete spandrel beams. These locations are indicated here in my vertical slice through the cladding. The Pearl Board insulation is a polyurethane foam board. The product is approximately 13 millimeters thick and is faced on both sides with a paper covering. The Pearl Board on the internal wall of the spandrel sections was, as already noted, adhered to a layer of plasterboard, as shown in this photo, with the Pearl Board being the top portion of this sandwich and the plasterboard being the bottom. I've not yet been able to determine if the Pearl Board on the ceiling was also faced with a layer of plasterboard, as I've been prevented from disturbing this product due to an apparent asbestos risk associated with the Artex plaster on the ceilings. Around the windows are UPVC window framing boards that form the final internal finish of the refurbishment cladding system. The location of these UPVC boards is indicated in this image. Here, 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 and importantly, as I've already mentioned, here in a thin strip. This image, which I've shown previously, shows a portion of a UPVC horizontal window sill and the vertical UPVC window jamb, by which I mean the side of the window enclosure, after the fire. This is shown in my vertical slice, again in yellow, above and below the kitchen window, as shown here. And again here in my horizontal slice at the side of the kitchen window. This slide shows a close-up image of one of the UPVC boards taken from Grenfell Tower. These had a smooth surface and were approximately 9.5 millimeters thick. As already discussed, there is an EPDM rubber weatherproofing membrane that extends between the edge of the refurbishment cladding window frame and the original reinforced concrete column. This is illustrated in this photo looking up at the building during the forensic deconstruction of the cladding that occurred following the fire, such that the rain screen cassette and insulation boards have been removed from the column at the left-hand side of this photo. The EPDM membrane is the material highlighted here in yellow. As you can see, this is a flexible sheet which was adhesively bonded to the existing reinforced concrete structure. The EPDM rubber membrane is highlighted in yellow in my horizontal slice drawing to the left of the kitchen window here. This image shows a roll of the EPDM rubber membrane and a single sheet of the material, both taken from Grenfell Tower and provided to me again by the Metropolitan Police Service. This product used the product used in the sections of Grenfell Tower that I've inspected is 1 millimeter thick, as shown. The window infill panels, as I've already discussed, are the non-glazed sections of the window units and are highlighted in yellow in this image. These are comprised of 2 sheets of aluminium, each with a thickness of 2 millimeters, and a polystyrene foam insulation core, 25 millimeters in thickness, and this is shown here. The smaller window infill panels that house the kitchen extract fans were similar to these, if not identical, in terms of materials and construction. That concludes my presentation of preliminary evidence as regards the geometry and materials of construction of the refurbishment cladding at Grenfell Tower. In the final section of my Part 2 presentation, I'd like to briefly describe the burning behavior of some of these materials. In discussing specific material burning behavior, which includes flammability, ignition, etc., I will focus on those materials which I consider to be most important with respect to the Grenfell Tower fire. Please note that I'm using the word materials intentionally here. At this stage of the inquiry, I will avoid commenting on the burning behavior of products other than to reiterate my previous statement that very little useful fundamental experimental data are available in relation to the burning behavior of composite products, since most products, again, violate the basic assumptions of many of the existing experimental and compliance methods. The discussion below is therefore based on samples of pure material. By this I mean a single material in the absence of coatings, protective layers, or incorporation into composite products. And this is actually a very important point. This is part of my preliminary evidence, this part of my preliminary evidence gives a very brief introduction to the reaction to fire of materials that have been identified to date as being present in the refurbishment external cladding of Grenfell Tower. I will present selected information based on data available in the scientific and technical literature rather than based on the specific materials themselves. However, in most cases, the information available in the technical literature has a strong dependence on the exact material formulations and test methods used. So at this point, these properties and values are provided simply for the purposes of illustration. I expect to study the burning behavior of a range of relevant products in considerable detail as part of my work, ongoing work for the inquiry, and also to comment in some detail at some stage on compliance testing methods which are currently used to assess the burning behavior of materials and products both within the UK and in European regulatory environments. Again, I will try to avoid technical language and jargon. However, again, the subject matter demands a certain level of technical terminology. Most of the materials of interest in this discussion are polymers. Polymers are synthetic or naturally occurring compounds that have large molecules made up of many relatively simple repeated units called monomers. Polymers are created by joining together the short monomer molecules to form long molecular chains. As already mentioned, a generic term to describe synthetic polymers is plastics. Polymers can be grouped, importantly, into two main types: thermosetting polymers and thermoplastic polymers. The differences between these two classes of polymers are, in my opinion, very important as regards the events that occurred at Grenfell Tower. A thermoplastic polymer will melt and can be deformed on heating, and in some cases can be returned to its original form. If heated under the correct conditions, the polymer will also undergo pyrolysis and will directly produce flammable gases. A thermosetting polymer will not melt on heating, but instead will thermally decompose, by which I mean undergo pyrolysis. These contrasting behaviors strongly affect how these different classes of polymers burn. Upon exposure to heat, a thermoplastic polymer will soften and melt. Once in a liquid state, the polymer may break down into constituent monomer parts. These may evaporate or pyrolyze to generate a flammable gas mixture. It is also possible for the solid to undergo direct pyrolysis to generate flammable gases. Thermoplastics may spread fire by burning as they flow or burning as droplets, as I've already mentioned. Since thermoplastic polymers will melt and flow, their reaction to fire is strongly dependent on their orientation. When burning in a horizontal orientation, a thermoplastic will melt and form a pool of liquid which will burn at a relatively steady state. In the vertical orientation, as I've already shown in part 1 of today's presentation, melting and dripping will likely dominate the burning behavior of a thermoplastic, and, as noted previously, contribute to the formation of a pool fire at the base of or in front of the material. Conversely, thermosetting polymers do not melt and instead chemically decompose, by which I mean pyrolyze, when exposed to heat. In this case, the pyrolysis process produces a flammable gas and leaves behind a solid char. The formation of this char means that some of the potential fuel is effectively locked up in the solid char and is therefore not available for releasing heat in the flame. The formation of the char also reduces the rate of heat transfer into the material, and as I've already mentioned, the pyrolysis rate subsequently decreases. Consequently, the gases may not be released at a sufficient rate to sustain a flame without some additional external source of heat, and therefore the flame may go out. The heat release rate of a burning thermosetting polymer is therefore typically characterized by a high initial value, as I've already mentioned, which rapidly decreases due to the formation of a char layer. I will now describe the burning behavior of some of the key materials found at Grenfell Tower in more detail. Both thermoplastics and thermosetting polymers were present within the cladding system in significant quantities. As we have seen, polyethylene was present within the Renabond PE ACM rain screen product, which was used extensively at Grenfell Tower, both in the rain screen cassettes and in the architectural crown. The polyethylene is highlighted here in yellow. Polyethylene is a highly flammable synthetic thermoplastic polymer. Upon exposure to heat, polyethylene will melt and drip, possibly flowing whilst burning or generating flaming droplets, as I showed in part 1 of my presentation. Its melting temperature is around 130 to 135 degrees Celsius, and its heat of combustion, which, to remind you, is a measure of the total energy that a material is capable of releasing under optimum combustion conditions, is about 46 megajoules per kilogram. Sure, you will no doubt have noted in the commentary in the media comparing the polyethylene material within the ACM rain screen cassettes at Grenfell Tower to petrol or diesel. This is likely to be on the basis, as I've already shown, that the heats of combustion of petrol and diesel are similar to the polyethylene used in Renovon PE ACM products. It's perhaps worth reiterating here, however, that the heat of combustion is only one of the important parameters dictating how a material will burn, as I've already discussed in some detail. Polyisocyanurate, or PIR foam materials, were also used in significant volumes within the cladding system at Grenfell Tower. And this was as part of the 4 insulation products that I've already discussed and which are shown here. The PIR foam is again highlighted here in yellow, so makes up the bulk of these products. PIR is a synthetic thermosetting polymer, which is primarily produced as a rigid foam. It has a very low thermal inertia, which you'll remember I discussed earlier. Its material properties make it extremely attractive for providing thermal insulation in buildings. However, the very low thermal inertia of PIR, as I've discussed already, means that it tends to have a comparatively low time to ignition and will support rapid flame spread without protection from an external barrier, for instance, an aluminium foil facing. The very low thermal inertia means that PIR may also accelerate flame spread of adjacent materials by preventing the loss of energy from the system. By this I mean by insulating, for example, the rain screen cavity and reducing losses, thus possibly accelerating flame spread. Thus possibly accelerating fire spread. The difference in terminology is actually quite important. The precise formulation of PIR foams varies by manufacturer, as does the manufacturer's use of different fire retardants. As a result, comparison between products in the available technical literature is not strictly possible. Nevertheless, to give you an idea of comparative hazard, the heat of combustion of PIR is about 26 megajoules per kilogram, or about 60% that of polyethylene. But this comparison must clearly be considered in light of my previous comments, noting the potential importance of other burning behaviors. I have already noted that phenolic foam insulation has also been identified in comparatively small quantities during post-fire investigations at Grenfell Tower. Phenolic foam is also a synthetic thermosetting polymer and is also primarily produced as a rigid foam with a cellular structure. Like PIR, phenolic foam has a very low thermal inertia, and consequently, it will have a comparatively low time to ignition and will support flame spread, again, when its surfaces are unprotected. As for PIR, the precise formulation of phenolic foams varies by manufacturer, as does the manufacturer's use of different fire retardants. Specific properties of phenolic foam are given in my Phase 1 report, but there's limited value in discussing them in this presentation due to the comparatively small quantities that appear to have been used at Grenfell Tower. Polystyrene foam is used within the core of the window infill panels at Grenfell Tower, as highlighted here. Polystyrene foam is a low thermal inertia thermoplastic polymer, and therefore rapidly melts at its surface when exposed to heat or flame. Once melted, polystyrene foam typically forms burning droplets or burns as a liquid pool. Its melting temperature is about 230 degrees Celsius, and its heat of combustion is about 40 megajoules per kilogram. Again, compare with polyethylene at about 46 megajoules per kilogram. Polyvinyl chloride, or PVC, is a synthetic thermoplastic polymer. With relevance to Grenfell Tower, I am discussing rigid PVC, commonly referred to as UPVC or PVCU. The U simply stands for unplasticized, meaning that the PVC is rigid at room temperature. Upon exposure to fire, UPVC may char. However, its particular chemical nature means that its heat of combustion is lower than for many other synthetic polymers. As a result, its ability to spread flame is also comparatively less than many other polymers. Its heat of combustion, for instance, is only about 18 megajoules per kilogram. However, the temperatures at which UPVC will soften and experience significant reductions of mechanical properties are very low in comparison with other construction materials. As a result, typical day-to-day upper service temperature limits for UPVC are in the range of about 50 degrees Celsius. Its melting temperature is between 75 and 105 degrees Celsius. This is significant, highly significant in my view, in the context of Grenfell Tower, because, as I've already explained, UPVC window boards form the initial barrier for flames to prevent fire spread from the kitchen of flat 16 into the cladding cavity beside the kitchen window. This issue receives considerable attention in my Phase 1 report. Ethylene propylene diene monomer, or EPDM rubber, shown here, is an elastomer or synthetic rubber. The chemical composition of EPDM rubber means that it will burn. No specific details were available regarding the combustion properties of the EPDM rubber used at Grenfell Tower at the time of writing my Phase 1 report. These will be studied by laboratory-based testing on an ongoing basis. Thus far, today, I've presented quite a large volume of technical information. I'd like to summarize the key points that I think are most important when considering the evidence as regards fire spread to and on the exterior cladding of Grenfell Tower. With regard to materials and geometry, the refurbishment external cladding system at Grenfell Tower has an extremely complex geometry and incorporates a number of different materials and products. Many of the materials and products installed within the cladding system are combustible, predominantly synthetic polymer materials. Particular features of the cladding geometry, which I have described during my presentation, resulted in the presence of a number of vertical cavities and channels within the cladding and running the full height of the building from level 4, from at least level 4, up to the architectural crown at roof level. As already noted, the architectural crown itself was formed largely from vertical channels of highly combustible Reynobond PE ACM panels. With regard to flammability and fire spread, whilst all of the polymer materials present are combustible, different polymer materials, as I've explained, can burn in very different ways and therefore prevent very different fire hazards under a particular set of conditions. The total amount of energy available for combustion is described by the heat of combustion, but there is no guarantee that all of this available energy will be released under particular fire conditions. A material's thermal inertia relates to how quickly its surface will increase in temperature when exposed to heating. This has consequences for ignition and surface spread of flame in particular. In the materials with a very low thermal inertia, such as PIR foam insulation, are likely to spread flame rapidly, particularly when their external surfaces are not protected by a metal facing. Thermosetting polymers like PIR will char on heating, whereas thermoplastics like polyethylene and polystyrene will melt. This again has important consequences for the extent to which the total energy available is actually released during a fire. And I've illustrated that again here with respect to the non-charring and charring behavior of various polymer solids. All of these ideas will become important during this inquiry as we try to unpick the respective effects both of the geometry and of the materials and products present within the cladding system at Grenfell Tower. These issues are central to understanding what happened at Grenfell Tower and to ensuring that it can never happen again. And that concludes section 2 of my presentation.
Thank you very much.
Mr. Chairman, thank you very much, Professor. This might be a convenient moment to take the midday break. I know that part 3, fire spread, will take a large portion of the afternoon, so it may be convenient to take an earlier lunch now.
Yes.
Whatever you're happy with.
Well, you've been on your feet for quite a long time. Would you like a break now?
Sure.
You
If that
probably
suits.
would, wouldn't
Yes.
you? Yes. All right. Well, we'll have a rather extended lunch break. If we resume at 2 o'clock, that'll give you plenty of time to finish your presentation, will it?
Sure, should do, yes.
Good. Well, that's what we'll do then. We'll rise now and resume at 2 o'clock. Thank you very much.